Hey everybody, this is Mr. Walsh, and we are going to talk about periodic trends today, which are basically patterns in the periodic table. We know that Mendeleev made his periodic table by looking at the chemical and physical properties of elements along with the atomic mass, but because he arranged things like this, he understood and he gave us the ability to understand that there's patterns in the periodic table that just kind of fall out because of his arrangement, because of electron configuration. If we're breaking this down, a trend is a pattern. Even a fashion trend is a pattern in how people dress. Okay, if somebody is trendy, they're kind of following the pattern of the popular colors and popular styles. Okay, and so a periodic trend is one that will repeat the pattern, and that repeating pattern is found on the periodic table. The reason why it's called the periodic table is because it repeats its pattern over and over and over again. Okay, and like I said earlier, Mendeleev organized all this stuff based on patterns. The first periodic trend that is kind of the basis of all the other periodic trends, or we're going to use it as kind of the excuse or the reason or the why for all the other periodic trends. And that's going to be atomic radius, or sometimes we'll call it atomic size. Okay, and so we can't measure, well, we can, but it's really hard. We can't really measure the length of just one atom, the radius of an atom. Okay, remember the cloud of electrons kind of makes this not a good sphere to do anything with. But what we can measure is what we call bond length. That is something that is able to be measured. So if you have two atoms that are of the same thing that are bonded together, we can take half of that, and that would be the atomic radius, assuming that you measure between the nuclei, which again we can do. Okay, so knowing how we measure atomic radius isn't as important as actually understanding what the trend is and how the trend works. And so it's important for us to understand where we came from on the periodic table here. Okay, so as you go down a group, okay, let's see. And so I guess the group that we're looking at is lithium, sodium, and potassium. Okay, so it's group 1, 1 valence electrons. Okay, and so the radius gets bigger as we go down a group. And I think this makes sense because what ends up happening is because we have more electrons, we have to have more energy levels that have electrons in them. So in lithium, the valence shell is 2, and that gives us one size. Now sodium, its valence shell is 3, and so now 1, 2, 3. So now this makes it bigger. And then potassium, its valence shell is 4, and now we have something bigger yet. So what makes it bigger as we go down the periodic table is occupied energy levels. Okay, or occupied shells. Okay, so the valence electrons are in the valence shell, so that makes it easier to understand that as we go down, the more shells we have with the electrons in it, the bigger the atom is. So if we were to look at group 1, the biggest element in group 1 is francium. The smallest element in group 1 is hydrogen. Okay, and that's true all the way down. Even if we look at oxygen, the oxygen family, the smallest element in the oxygen family in terms of size is oxygen, and then the biggest one is element 116, which on this periodic table isn't named. Okay, but if you put polonium looking at this periodic table, that's fine. These are the types of questions you'll see. Which element is the biggest? So in this case, we want to know which one is the furthest down on the periodic table. Okay, So O, S, SE. Okay, SE is the biggest. Okay, CLBRF, CLBRF, so it looks like BR, BA, BE, CA, BA, BE, CA, so that's group 2, so that's BA, and TA, NB, and V. Even though we haven't really talked about these things, we have tantalum, let's see, tantalum, niobium, vanadium. So tantalum, again, is the biggest, okay? And notice all of these groups. This was group 16, and this was group 17, and this was group 2, and this was group 5. So they were all in the same group, so we were just comparing elements within the same group. So what happens as we go across the periodic table? Okay, so here's what I'm going to say. Let's look at period 2, lithium, beryllium, boron, carbon. Okay, and I will tell you that the trend is they get smaller, okay, smaller as we go across, okay. That's what the trend is. The reason why is because the number of protons. So lithium has 3 protons to pull in 3 electrons. Okay, so that's going to pull a certain amount, a certain distance in. These electrons get pulled like an electric, like a magnet, right? And so these 3 electrons are going to feel the pull of 3 electrons. Now, beryllium has 4 protons, has 1 more proton. So now these electrons are going to feel a bigger magnet pulling them slightly more close to the nucleus. Boron has 5 protons, so they're going to feel even more of a pull, a bigger magnet. Now we're at 5. Now by the time we get to carbon, we have twice as many protons as where we started, and so now we have an even bigger magnet to pull these electrons in, even closer to the nucleus. So as we go across, because the elements get smaller because of the number of protons. And if we wanted to get really creative, we could go back to the beginning and we could say the number of protons is equal to the atomic number. So as long as they're in the same period, the bigger the atomic number, the smaller the atom. Okay? So bigger the atomic number, the smaller the atom, or the atomic radius. Okay? So it's kind of seems a little counterintuitive because you're like, oh, it has more electrons, so it should be bigger, but that's not the way it works. Now we have elements that are all in the same period. Okay, these guys are all in the same period. So now we're going to look and see which elements are the biggest. They don't always have to be the biggest. I may ask which are the smallest. I'm not trying to fool you here. Just make sure you read the question so you know. So let's see. Sodium, magnesium, aluminum. So as you go across, they get smaller. So the biggest one is sodium. Carbon, oxygen, neon. Carbon, oxygen, neon. So as they go across, they get smaller. So carbon is the biggest. Wasau. Tungsten, osmium, gold. Okay? Just because they're in the transition metals, tungsten, osmium, gold, that doesn't mean it doesn't follow the rule or the pattern, right? The periodic table is amazing like that. The pattern holds no matter where we're dealing with. So tungsten, osmium, gold. So the further to the, let me say it differently than I have been, the further to the left, the bigger it is. So tungsten. And then BRKRAS. BRKRAS. It looks like arsenic is it. Is the general trend for atomic radius. And we did this, right? The further down we go, the bigger it is. And the further to the left it goes, the bigger it is. So the thing that is in the bottom left-hand corner of the periodic table is francium. and the thing that is in the upper right-hand corner is helium. So francium is big, and helium is small. Okay, and I'm not going to ask you questions about things in the same period or things in the same family. I'm going to ask you about elements that are close to each other, and then you're going to have to take and figure out which one it is. Okay, so here again, I'm asking you which is the biggest, but it could also be the smallest. Okay, so I'm not trying to be weird here. Okay, so let's see, CNSIP. So CNSIP, and we want the biggest one. So we want the one that is further down and more to the left. So that's going to be SI. The other way that I like to do this, okay, is I'll look at this. I'll go C versus N. Which one's bigger? Okay, C. So N can't be it. C versus SI. Which one's bigger? SI. SI versus P. Which one's bigger? SI. So that way you've compared all of them and you know that SI has to be the right choice. Cl, Br, S, and Se. So Cl, Br, S, and Se. So we compare Cl versus Br. Br is still it. Br versus S. Br is still it. Going up and down is way more important than going left and right. Okay, and then Br versus Se. Se is bigger. Okay. Ba, Be, Na, Cs. Ba, Be, Na, Cs. So the choices between Cs and Ba, and again, we want the one that's closest to francium. We want the one that's furthest down and most to the left, and so that's going to be Cs. And then Cu, P, Ge, Ga. Cu, P. Cu is still Ge and Ga. Cu is still the furthest to the left. So there's that. So if you understand size, then we can do the other ones. And the last video is going to have 2 more trends. And the reason why the trends are the way they are is because of size. So now we know how size works. Now we can go and we can talk about other periodic trends.